Hello and welcome back. So, in the previous video, we were discussing about natural number systems. So, first we discussed about natural numbers and we proceeded to discuss about integers as well. So, what we saw is that the natural numbers are an example of what we call a countable set, and there are infinite number of elements in this countable set. But and also we discuss the definition of countable also involves natural numbers in a way that when you call something as countable, what you are actually doing is you are assigning natural numbers to the objects that you're counting. For example, you have some objects like this, and you want to see whether you can count this or not. So what you can obviously do is take these natural numbers and assign them one by one on these objects. As you can see, you can start from one and you can means all the uh, objects that you are counting have a natural number assigned to it. So that's how we count. And you can see this is a countable set of objects. Now, even if these objects are infinite in number, suppose there are many more stars, you'll still be able to continue assigning natural numbers. And the good thing about the natural numbers is that you'll also not never run out of natural numbers. So doesn't matter how many objects are there or if it runs to infinity. For every object in this sequence of objects, you will find a corresponding natural number, and that is what is an countable infinite set. And in our number systems as well, we have such sets. For example, a very good example is integers. Now you might first think that number of integers is actually much larger than the number of natural numbers, but you'll soon realize that's not true. You might be tempted to think that because you see natural numbers are just contain the positive numbers, and integers along with these natural numbers also contain all the negative integers and zero, so must be big, right? But that's not the case, because here also if you just simply rearrange these integers like this, you can see you can still assign to each of these integers these natural numbers. And how do I say that integers is not larger than natural numbers? Is that there will never be an integer where you cannot assign a natural number. So as you go on like this, for each and every integer you find, you will still have a natural number. And vice versa. For every natural number, there will be an integer on this set. So even though the sets seem of very different sizes, but they are actually the same size, and that's very surprising. Right? That's how infinities work. Both of the number of elements of natural number and integers is infinite. Hmm. And those two infinities are equal. And natural numbers is equal to number of elements in integer. Now what else can you think of that we can check the countability of these natural numbers and integers? Hmm. By the way, this ensures that this integer is a countable infinite set, because if you have equal number of elements in the set as natural numbers, obviously you can just arrange these the both sets side by side, like these are the natural numbers and these are the integers. You can arrange them side by side and you can always correspond each and every element with each other. So Both of these elements are countable infinite set, and integer and natural number both are uh, mm, equal, have equal number of elements, so which is also called known as the cardinality of the set. And also the way we are corresponding element by element, this correspondence is called mapping. So when we do mapping, we actually correspond from one set to the other. For example, we are corresponding the natural numbers uh, to the integers. So we can say, for example, what is the first integer or second integer, fourth integer. If we write like this, then we can answer these questions, and that's what is called mapping. And this is a special type of mapping in which each and every element of both sets are linked with each other. This is called bijective mapping. So a little side note here. Bijective mapping is when you have these two sets and you're trying to correspond the elements of one set with the other. So, so for example, there are some elements in this set and there are some other elements in this set. Each element of set 1 is corresponding with another element of set 2, and that is bijective mapping. And as you can see, this is only possible when the cardinality of these two sets are equal. So when the cardinality of the two sets are equal, it is possible to have a bijective mapping. And this is how we will check whether some other sets are countable or not. Let's see, like this is surprising enough that natural integers are equal in number with the natural numbers. Let us now have two uh, sets of integer in a plane. For example, you have a plane. You have two integer axes arranged like this. So this is an integer axis. So 0, 1, 2, 3. So now, for now, I'm not considering any points in between. I'm just bothered about these integer points. So I'm bothered about these points, and also about these points. So we can write each and every point in the points that I'm marking, like what is it in the vertical axis and what number does it correspond in the horizontal axis. So for example, if I take this point, for example, if I name this point A, this corresponds in the horizontal axis, it corresponds to the number 2, and it corresponds to number 1 in the vertical axis. So I will identify this point by writing 2 comma 1. So, and not only in the positive side, it extends in the negative side as well. So uh, you can understand there are infinite number of such points, which fall in this integer plane. And uh, let's find another example. For example, some a point like this. So how will I identify this point? So this is this point corresponds in the horizontal axis with -1. So it will be -1, and in the vertical axis it corresponds to 3. So it will be -1 comma 3. So this is how I am identifying these points. Now this set can be represented like integer, two integers having this is what is called a Cartesian product. So, Cartesian product. So What is this product? So this creates a new set where I have all the elements which are some A and some B, A comma B, which are these representations that I was talking about, in such a way that this A is an integer and so is B. B is also an integer. Okay, so for all integers, uh, if I write them in these brackets, so these fall inside this plane. Now what I want to do is I want to count them. I want to count this set and check whether I can assign natural numbers to it or not. That is, I want to check whether the set is countable or not. So let me try listing it. Let me try listing the set. So you can see that you have this origin point 0 0, and as you go this way you have 1 0 2 0 and so on. As you go this way you have -1 0 -2 0, so on. And as you go up you will have 0 1 0 2 and so on, and at the bottom you will also find a lot of points. As you can see, I'm not getting anywhere near to counting these all numbers. So it goes on in all directions. It goes on in all directions, and it's just hopeless. I cannot uh, think of counting it like this. Then what I will do, I will try to find a way to rearrange this in a single line such that, like for example, what we did with the integers, we rearrange this in a single line in such a way that we can start counting these numbers. So what is the way that we can do this? So for example, let's have this 0 comma 0 at first. So we have this 0 comma 0 at first, and taking inspiration from the integers, we uh, just move all these negative points in this side, and we alternatively write the positive and the negative numbers. So if I write like this, you can see at least this line is covered, right? So this is basically what we did with the integers. So now what I will do the same thing with the vertical axis. So I'm alternatingly writing a positive and a negative integer, and that covers the vertical axis, as we can see. But there are so many other points here. How do I include this? So I also write these here. So here the vertical axis coordinate is 1, and I will just write whatever the horizontal uh, coordinates I come across. So sorry. So this is 1. So all vertical axis 1 points I am writing in this line. So all vertical axis 1 points I'm writing here. So and so, and you get the drill. And so here I will have this minus, so 1 minus 1 and so on. So this will be 1 comma 2, and I can continue like this. But this is also very difficult to count. For example, if I just straight away without thinking anything just start counting, and I assign this as 1, and assign this as 2, assign this as 3, I will never finish this row. I will never finish this row. I can never think of coming to the second row, because there will always be more and more points in this row, uh, and uh, to skip to the next row is almost impossible. So there is a way to address this problem, and it's like counting through a very zigzag motion. So what I do is assign this as 1 and then move diagonally like this and assign this 3. Then I go down, assign this 4. Then I do this zigzag motion. I hope you can follow the pattern. So this is going like this. This is in a zigzag way. This will ensure that all numbers are covered. So this is 4 and this is 5. This number is 6. This is 7. This is 8. And if you count like this, you notice that you are moving in this approximately this direction, and each and every of these points will be covered, and each and every point, however large or however further away from origin they will be assigned a natural number. And this is how we can also conclude that this z cross z, this is also a countable infinite set. And since it's a countable infinite set, that so each this natural numbers and this z cross z set have a bijective mapping. We talked about what is bijective mapping just a little bit earlier. So they have a bijective mapping because they are countable. Like I am literally assigning natural numbers to these points, so they are countable infinite. So they have bijective mapping, which is each element is corresponded. Each natural number element is corresponding a uh, single point in z cross z, and so and we also saw that in this bijective mapping, when you can correspond each and every point to the other, and there will be no natural number left, because for every natural number also we will have a point because it runs to infinity. So we must have the number of elements to be same. We must have the number of elements to be same. We can represent the number of elements like this. So number of elements of natural numbers is equal to the number of elements of this. Okay, so how crazy it may sound, but if I have a plane full of points at discrete locations, at integer locations, so I'm not talking about the points in between 0 and 1. So those will be real number points. We will come to that at a later video. But I'm only taking the integer points, but these are also infinitely many, and you can see the number of such points will still be equal to the number of natural numbers we have, and that's a very interesting result. So thank you for listening. Come back later.